Okay, so inside the ball, okay, this exponential, this mapping is 1 to 1. Okay, so for every rotation, there's a unique omega. Okay, on the surface of the ball, okay, this exponential mapping is 2 to 1. Okay. All right. So let's write antipodal points. Antipodal points represent the same rotation. Okay. All right, so this assumes that we're restricting the angle, theta, to be between 0 and pi. Okay? So you can ask the question, what if we just ignore that restriction and just let theta be anything? Okay? Okay, so what if we allow theta to be, say, 0 to 2 pi? Rather than between 0 and pi. Okay? In that case, we have a solid ball representation, but in this case, the solid ball is of radius 2 pi. Okay, so let's draw the ball again. Okay, so let me draw a ball. Here's the center. I'll draw another ball in the middle. Okay, so it's something like that. Oh, there we go. Okay, so it's a solid ball of radius 2 pi. So this is pi. This is 2 pi. All right, so let's take, say, this point. Let's say this point is inside the solid ball of radius pi. Okay, so we have this vector omega. Okay, so what this represents is a rotation around, right, this axis. Okay, let's call this omega. So it's a rotation around this axis by angle omega, right? But now, if we go in the opposite direction, okay, so let's go in the opposite direction. Let's travel a distance, say, pi from here. So to this point. Okay, so you see what that see what's going on here? So this point is inside the ball of radius pi. This point is outside the ball of radius pi. Okay, and the distance from here to here is pi, say. Is pi. Okay, so now what does this represent? Yeah, 2 pi, sorry, 2 pi. Oh, no, wait. Pi. No, it's pi. It's pi. Wait, let me think. Pi. I think it's 2 pi, yeah, 2 pi. Okay, so 2 pi. Okay, so this point represents the same rotation as that. Okay? So these 2 points, this point and that point, okay, represent the same rotation. Represent same rotation r. Okay? So in this case, we have a 2-to-1 representation. Okay? So we have a 2-to-1 representation inside this solid ball of radius 2 pi. Okay. Okay, so we don't need a 2 pi radius ball. Pi is enough. Okay. Well, you can see that if we allow theta to be in any range, then this ball just gets bigger and bigger, right? And then we have multiple representations. So every 2 pi, okay, represents the same rotation. So we'll just cut it at pi, okay, and get it 1-to-1 inside, 2-to-1 on the surface. Okay. All right. Some notation. I wasn't explicit about this last time. Okay, some terminology. Okay, so when we have in our relation r is the exponential of omega, we're going to say that omega is the logarithm of r. Okay, it's the log of r. Okay. So when we talk about the log of a rotation matrix, okay, this is what we mean. Okay, it's the omega here. Okay, exponential log is natural. All right. So as I mentioned last time, it turns out that this exponential representation is going to be very useful for us later when we talk about the forward kinematics of arbitrary robots. Okay. But we're going to come back to that maybe 1 or 2 lectures down the road, maybe 3 lectures down the road. What I want to do is I want to now cover positions and orientations. Okay. First do it in sort of the conventional way. And then we'll come back, see how this exponential representation can help us, okay, study rigid body motions.